So for anyone who's joining online, I'm starting the recording now, just so you know. And cool. All right, so basically, Dr. Vassal was asking me to go through the homework that you just turned in last week, and then answer questions there. And he gave me a couple extra problems to show you, and then also the questions you had last week that I went and found out those. So I'll start with that. Make sure I can write on here. Cool. Okay. Yeah, so last week, I think there were like 4 questions, I believe. So I'll just go through those real quick so that y'all know. I think it was you who asked me. The compressible flow and how that affects your Reynolds number. So Reynolds number, right, is going to be rho v L over mu. So essentially what Dr. Vassal told me is that Reynolds number is based on a characteristic length, right? So you were sort of picking like a reference frame for that length to base that on. So that L is a reference value. And so in the same way, you can pick your density to also be a reference density. Gotcha. Yeah. So the eraser gets me every time. So you can also pick a reference density. Or you could like calculate Reynolds number for a bunch of different points at a bunch of different times. And you can have like a Reynolds number field that varies with time and space too. So, but then he also wanted me to mention to you that, so I can write reference or vary with time and space. And I'll say, but whenever you're in like it doesn't have to be supersonic, but just a compressible regime where the Mach number is 0.3 or greater, the Mach number becomes more important than the Reynolds number, or more relevant, I guess, because it's at those sorts of flow speeds, that Mach number is going to tell you more about the characteristics of your flow than Reynolds number does. So like, not to say it's not important, it is important in some scenarios, but right, less applicable. Yeah.
And then just one other question. So obviously then like rho and L, like for a field of like time and space, like rho and L are always going to be related, right? So it'd be like, if you pick an L of like 0.05 meters, like if you're going to pick the rho with that subsequential length, right? Like at that point.
Is that just if it's compressible?
Yeah.
Right.
Yeah, because incompressible rho doesn't switch.
Yeah. So let me write that down. So, so yeah, for the compressible regime where your Mach number is greater than 0.3, that's what we're talking about here. And so that density, like let's say an airplane, for example, your characteristic length might be like the chord length of the wing. And then you might, like along the wing, you might pick points on the leading edge and points on the trailing edge. And then calculate the Reynolds numbers for those points, and then iterate through time and track the change through time. But your characteristic length would still be the chord length.
Okay.
Yeah. So I'll say Mach number more relevant. Wait. than the Reynolds number. All right, so that's that question. And if you have anything, just interrupt me if you have questions. And then for number 2, someone was asking about the transition regions for when you go from laminar to turbulent flow and the Reynolds numbers that associate with that. So it's going to be dependent on the geometry that you're working with. So a pipe is different than like a flat plate, let's say. And you could also think about that as those are your boundary conditions. Your geometry is like a boundary condition. So I think last week I said something like 2,000 to 3,000 was your transition region. That's for a pipe. So if we have a pipe, then oh, there it is. So if we have a pipe, then I'm going to draw like a x-axis where this is our Reynolds number on that axis. So the laminar region is over here. We have a transition region between laminar and turbulence on the right. So the laminar region starts getting into transition at 2300. So that first mark is 2300, and you start getting into pure turbulence at 3500 for pipe flow. And then for a flat plate, which is another like super common one that you're going to see, that one's going to be, they didn't really give, when I did some searching, they didn't give the same, like the transition starts here and ends here. They just said that somewhere around 500,000 Reynolds number is where you're going to see the transition. So it's very different. Yeah. Yeah, very different. Oh, that was terrible. Let's rewrite that. There we go. Yeah, so 500,000, that's where you're going to see that transition.
Is there, just out of curiosity, like, do you find any reason as to like why, like what about the geometry makes that change that drastic, or is it just like one of those constants?
I'm not sure what it is about the geometry that changes it. I can find out for you though,
No, I'm
if
sure
you want me to.
to.
Okay.
Yeah.
Yeah, sounds good. Yeah, I don't know exactly why those boundary conditions make it vary that much.
Yeah, I just didn't
But
expect 500K after.
yeah, exactly.
So when you're in the transition period, is that meaning that like some of the flow is laminar and some of it's turbulent, or like what exactly does the transition mean?
Yeah, it's like you have this hybrid between laminar and turbulent flow where it's starting to leave laminar and become turbulent. So it's not exhibiting like pure turbulent behavior, but it's not purely laminar either. You've got this sort of like mixture where it's transitioning.
So are most flows in the transition, or are they just turbulent?
Are most flows? I think it really depends, especially on application. Like I'd say most things like with an aircraft, you're going to see probably turbulent flow, I would assume. Yeah. To be honest, I don't know. I guess you just have to run the numbers in whatever scenario you're in and see where that number's falling. That's a good question, though. I can ask for you if you want me to. Yeah, I'll ask. Yeah. That's good. I would say most of your flows will not be laminar, if I had to guess.
It's like very hard to like even simulate it, right?
Yeah, laminar is pretty rare from what I gather. But you know, that transition region versus turbulent, I'll find out which one's more common.
Start doing research for you.
I do research all the time. Literally is my job. All right. Okay. So, wait. Oh, no. Well, I'll rearrange these later. Somehow I started on slide number 3. So the third question was, we had this like plane and we had that block sliding down it on a film of oil, right? And so we've got this oil that this block's sliding down. And there was a question about, is there a buoyant force in that oil? So technically, yes, there is, because that oil will depress, even if it's just like a micrometer, it'll depress. And so you'll have a buoyant force, but it's so minuscule that you don't include it in the calculations.
And I had another question about that. 'Cause,
Yeah.
Like, from my intuition, density probably affects buoyant force, right? Like something with a greater density would have a greater buoyant force because it's gonna be harder for an object to pass through it, right?
Mhm.
So if that was like a denser liquid, would it be something we have to consider?
No, I don't think
Okay,
so.
it's
Yeah,
just that
yeah.
something that small of an application is just as negligible.
Right,
Okay.
right. Yeah, and the point Dr. Vassal made was, you know, this thickness here is like on the order of like, you know, maybe a tenth of a millimeter.
Yeah, like a nanometer.
Right, yeah. I mean, it's so small that even though there is technically a force there, you can just
Yeah, it
ignore it.
doesn't matter.
Right, exactly, yeah. So, so I'll say, technically, yes, buoyant force, but so small. Disregard it. All right. All right, and number 4. So pretty much same question, block sliding down that ramp. So I'll say, same scenario here. The question was, why don't you see weight affecting your shear force? Like if you had a really heavy block versus a lighter block, then why would your shear force not be increased? Like, because your friction force would be, right, if you have more weight. And so the way that Dr. Bassel explained it to me is that friction is a solid to solid interaction, whereas shear is a solid to liquid interaction. And
shear is dependent on viscosity.
right. You mean because it's liquid?
Yeah.
Yeah. So shearing is when that fluid is deforming under. So shear is just like pressure applied in the trans. What's what I'm looking for? Not axial, but in parallel to the plane, planar, I guess. And so transverse, maybe you could say. And so when that transverse force or a stress is applied, then you have deformation in that liquid, and that's where viscosity comes into play. Is that deforming, and how sticky is that fluid that's deforming? Yeah. So the way that Dr. Bassel explains to me is that weight will affect both of these. So weight still affects both. The way that it affects shear is that because you have this tau is equal to viscosity du dy formula, the weight is going to, in your force balance, that's going to affect the speed of the block, right? Because the weight of the block will affect your acceleration.
Increase weight, increase du dy.
Right, exactly. So weight indirectly, you might say, is going to affect the du dy. So, and therefore, it affects the shear. So it's kind of a backwards way of getting to it, but yeah. So that's the explanation he gave to me. Okay, so, and I'll just write here, why no let me see, let me do it this way. All right. All right, is there a buoyant force? Okay, so there's those, and I'll rearrange them later so they're actually in the right order. But so now there's two questions Dr. Vassal gave me to work with these like rotating discs with fluid in between them. And so I thought that I would give you an example of like where you'd see this in the real world kind of thing. So this is a turbine blade for like the power generation system. And so this is a conventional turbine blade where you have these like, all these blades at an angle. And so when your fluid flows through, it's pushing those like a propeller on a boat, moves the boat forward kind of thing. But so this is not what we're talking about. What we're talking about is something like this. This is called a Tesla turbine. And so instead of having these blades that the water physically pushes on to make it turn, the fluid is coming in from that inlet and it flows between all these discs. And the force of the shear from the fluid in between the discs is what's actually turning that turbine. So it's all shear driven. There's no like actual physical pushing on blades to make that turn. So
Sorry.
yeah.
Back to that other slide.
Yeah.
You said that's for power generation?
I believe so.
Thermal cycle,
Mhm.
or something like that.
Yeah. So like if you go to a power plant, you're going to boil your steam or your water, make steam. Steam goes through that, and then it's going to turn that turbine. That turns a generator, and the generator's making the power.
So would that be like probably two into a bit like a Rankine-Brayton cycle?
I don't know. It's been a second since I've had that class.
Start speaking of down it.
I just had that class as well.
Oh, did you? Yeah, I have to go find out for you. But I mean, I would say that this is, at least from my experience with power plants, they have something like this, where they're running the steam over these blades.
I didn't realize it was so huge.
Oh yeah, they're gigantic. Yeah.
When I draw the problems, my boxes are like that big.
Yeah. That's they'll have multiple of those kind of thing, and then they're running steam through all those, and they're each attached to a generator. And these generators are like 20 feet in diameter, 15 feet tall, basically as big as that, but it's just a gigantic electric motor essentially. Creating- yeah. I mean, probably not much more. No. Anyway, so, yeah, you said Rankin or Braden cycle. Yeah, I'm not sure I ever covered Braden cycles when I was in Thermo 2, but I mean, a Rankin cycle, from what I remember, would fit something like this. Yeah. So. Okay, so problem 1. Okay, so essentially we have these 2 disks. They're rotating at a constant rate, but different rates. They're rotating the same direction, but one's going faster than the other. And we're wanting to determine what the torque is to sustain that motion so that the resistive forces don't cause those disks to stop rotating. And so we know the gap is 0.1 millimeters. We have SAE 10 oil filling the gap. And then we know our viscosity for that oil that's given. And we know our velocity profile is linear. So for the givens, I'm going to write omega A, 50 radians per second. Omega B is 20 radians per second. We know our gap is 0.1 millimeters or 0.0001 meters. We know we have SAE 10 oil with a viscosity equal to 0.02 Newton seconds per meter squared. And our du dy is linear. And we want to find our torque. Okay, so in the lecture, Dr. Vassal derived an equation for you. And that equation was M, which M is actually your torque. So I'll just write either one, T or M. So T or M is equal to pi omega r to the 4th mu over 2h. Oh no. Yeah, that's after the derivation that he did in class. And so essentially this problem is just plugging in these values that were given. So we have this formula. So we have pi. Omega is the relative velocity, the relative angular velocity. So this is going to be 50 minus 20 radians per second. And it's worth noting here that the reason we're subtracting these is because they're turning in the same direction. So this would be like if you're on the highway and you're going like 70 and someone else is going 50. If you pass them, it's like they're sitting still and you're going 20 miles an hour, right? But then if these were going opposite directions, then we would add these values because that'd be like passing someone going the other way on the highway. And it's like they're sitting still and you're going 120 miles an hour. So, relatively. So, yeah, so I just figured I'd mention that.
Oh, my relative speed is only 60. So you're doing 150 miles per hour.
Okay, so then our radius. Oh, we're actually given a radius here. So All right, R. It's that guy. So our R. I did not leave enough room here. Okay, so pi 50 minus 20 radians per second. R is going to be 0.1 meters to the fourth power. And then our mu is going to be 0.02 Newton second per meter squared. And all of that is divided by 2 times h, which is 0.0001 meters. Okay, and then if we cancel our units, so we could rewrite this guy as put a fourth power there and a fourth power there. That's what I use to make sure I don't like start canceling stuff and then forget that that 0.1 is also the fourth power. So right like that. So those 2 meters squared can cancel with 2 meters squared there. This guy can cancel another meter. And then we have seconds with seconds. And yeah, okay. And then what we're going to end up with is this will be equal to 0.942 Newton meters. That's our M.
Go back, bro.
Yeah, sure.
So I did it a different way.
Mhm.
And instead of having 2 in the bottom, I had 2 in the top. I had 2 pi
Okay.
times 30 radians.
That's another thing also I was confused on is if you only have pi in the numerator, will it not cancel out the radians? Because to get out of radians, they have to multiply by 2 pi.
So if you were going to, so you're talking about like converting from degrees to radians?
Yeah.
So radians is a dimensionless quantity. So when you have radians like that,
I was talking
yeah.
from radians to revolutions per second, I think it is. It's times 2 pi, right? Pretty sure that's what it was. We did the solution together. What do you know?
yeah. So like if you, so you're saying like if you had, let's say RPM
Yeah.
and you want to convert to radians?
Yeah.
Yeah. Okay. So like if you had, I don't know, 10, no, let's not use 10. If you had like, let's say 4 RPM, that's going to be 4 revolutions per minute. So you could say 1 minute is 60 seconds. And then say 1 revolution is 2 pi radians. And that would leave you with radians per second.
Yeah, because the way we solved it, like I'm looking at this thing right now because we did it together. So we took like the area as being pi r squared, and then we derived it. So we got dA, and that was 2 pi r. And then we used that with yeah, it'll be easier.
They did it closer to what he did in class with the derivating with like dA and d and stuff.
So I'm actually about to work the homework problem that does this derivation. That might help.
Okay.
Make it, yeah. That might. Do you want me to do that right now?
No, you don't.
First?
You
Okay.
you don't have to. I don't want you to like jump around. We just want to make sure that like we still are like doing it and accept because we got the right answer, but like we just want to make sure the way we got there is acceptable.
Yeah. So I guess what you did is you derived it. I
Yeah.
guess right, and then plugged in.
Exactly.
Right. So I guess for this problem,
It just jumps the gun.
yeah, he just said here's the formula that you just derived, and so just plug in, and then you're good.
And out of curiosity, do you know like on exams would he like provide that to where like he'd say like, hey, this is the formula that you need to use here, or sort of like we know that from the derivation? I know it's early to ask that, but
He hasn't told me anything.
Okay.
I would ask him if he's going to give like a formula sheet or if he's going to do like a open book
Yeah.
or whatever he's going to do.
I'm just curious, like,
Yeah.
obviously we'll study differently depending on which one he says.
Mhm. Yeah, I would just say, just ask him,
Okay.
yeah, what kind of references he'll give you. But yeah, you're good.
Because we have point or 2 pi times 0.02 times 30 times 0.1 to the fourth over 0.0004.
Can I see it?
Yeah, I'm gonna work out
Or
here.
maybe it's just, maybe we just have ours arranged.
So you have mu times omega times r to the fourth times pi divided by, are these the same quantities? Yeah, okay. So you have, so there's like an extra 2 down here
Well, we had the 2 pi
in the numerator.
And doesn't, I just worked this out, unless we forgot. Yeah, I did it wrong, but I think it's about even. I'm gonna come that way. Let me know if you get like 0.2 for that. I don't know if I did the denominator properly. I hit that with calculators.
Oh, I see what it is. This right here, that 4, if you factored out a 4, the 4 and the 2 cancel.
Okay.
And you have 2 in the
So it's
denominator.
just the way we derive it. And it's
Oh, yeah.
Yeah.
Okay.
You have 2 on the numerator and then a 4 in the denominator.
Okay.
And I just have, yeah, it reduced. Cool. Any other questions about that one? Or- No, you're good. You're good. I'm here to answer questions because,
Rather do it now
Yeah.
than on the exam.
oh, no, for sure, for sure. This is the kind of stuff like that I need to, like whenever I'm going through a class, is like asking the questions that maybe like no one else needs that, but like I need that, you know? And then everyone else is like, oh, okay, that actually, I needed that too, you know, so. Yeah, oh, for sure, for sure. Because ultimately you want to understand it to where you're not just memorizing it, you know?
Oh, yeah.
So. Yeah, so I'll just say, just so no one's looking at this like, what is this? I'll say conversion example. Okay. All right, there's our turbines. Okay, so problem 2. So in this one, we have 2 disks again. One is stationary and one is spinning. And again, we want to find the torque to sustain that motion so our resistive forces don't stop the disks from turning. And then we're going to plot that torque and we're going to plot the torque and then versus the gap thickness. And we know that we have the oil, the same oil, SA10, with a viscosity of 0.02 Newton seconds per meter squared with a linear velocity profile. So again, we have omega A, this time it's 0. Omega B is 20. We know we have a T value that is going to vary between 0 and 0.1 millimeters. And then we have the same oil with a viscosity equal to 0.02 Newton seconds per meter squared. And our d u dy is linear once again. And we know that our r from the figure is 0.1 meters. And we want to find our torque, or M, all right, the same way, T equals M. Okay. So this one's very similar. It's the same equation as before. So solution, part A. Put over here, part A. So again, m is equal to pi omega r to the fourth mu over 2h. And so that's going to be just now plug in our values. Pi times 20 minus 0 radians per second. R to the fourth is going to be 0.1 meters to the fourth power times 0.02 Newton seconds per meter squared over 2 times. Now I would put, before we put a value, but in this case, we're just going to put t since it gives us a range. Yeah, and plus we want to plot it here in a second. So I'm just going to put t there. And so, I mean, that's essentially your answer. You could go ahead and like simplify that if you wanted to. So I simplified it as 20 pi radians per second times 1 times 10 to the negative 6 power. And then if you kind of simplify your units, you'll end up with well, the units get kind of weird because you're not plugging in that t value, but yeah, I suppose do what? Yeah.
Could you go back to the other one and explain like how they cancel out?
Yeah, sure. Yeah, so this one you end up getting like Newton meters squared, but then because you have this t in the bottom, then you end up with Newton meters once you plug a value in there. Yeah, so that is essentially the answer to part A right there. Okay. You want me to go ahead and go back to the,
Yeah, or you could just do
Yeah.
like a big blank slide if you want and just like erase it when you're done with it. Like you don't have to go back to it and do all that.
yeah, no, I'll go back to it real quick. So, okay, so here's, I'll use the same slide. So what do we have? We had pi times 30 radians per second times 0.1 meters to the fourth power times 0.02 Newton seconds per meter squared, all divided by 2 times 0.0001 meters. Okay, so what I did, this is a trick I do for myself, but I take that fourth power and move it in to each term or each, I guess, portion. Otherwise, sometimes I'll forget, like, did that. Yeah. So I'll put a 4 here, 4 there. Okay. So, yeah, so what I did is I said seconds. Let's do this. Okay. Seconds and seconds cancel.
I pretty much get everything except for the radians. That's what I know. Because I know
Oh,
obviously
okay.
what we're looking for in the end is like, 'cause I know like, okay, seconds and seconds are going to cancel. Then
Yeah.
you have meters, that's the fourth in the top, right? And then you have times meters squared. So it'll go to meters, just meters, right? Because you have a meter at the bottom and you have a meter squared in the denominator at the top.
Yeah.
But like how from with the radians do you get to, because it's Newton meters, right? For to work. So like, how do you get there?
Okay,
Like,
so
I just
you're,
don't get that jump.
yeah, so you're just saying like, why don't you have Newton meter radians?
Yeah.
Why do you just have
is-
Newton
yeah,
meters?
like, why is radians still in there? Is it because it's rotational or like, does it cancel out?
Yeah, I'll show you. I'll show you. So, yeah, so I'll just mark it like this. So seconds, seconds, that, and that guy, and that guy. And so then what that essentially leaves us with is that we're going to have radians times meters times newtons. That's all that's left. So radians is I guess radians, I think of it as like a placeholder. It's essentially like you're saying per second. It's not really,
Okay.
it's kind of a weird thing, but radians is essentially like not there.
It's not a unit itself. It doesn't
Right.
hold any like value for the.
Right. Yeah. So once you convert to radians,
So is that there, like, would that be considered a rate of change? Because like, it's like per seconds, like, would that be considered like a rate of change, or like, how do you like look at it? That's the only part I don't really understand about the problem.
okay, sure. So your question is, what is the significance
Yeah, the
of that
significance
radian
of the
value?
radians. I get that it's like unitless, but like it being there, does it mean like it's gonna change with rotation, or it's gonna change with time, or like?
Okay, that's what you're saying. Yeah, so the times canceled out. So
Yeah.
it's not changing with time.
Yeah.
But so this is saying that, so 30 radians per second, 2 pi is roughly what, almost 6.5 kind of radians. So this is sort of like saying maybe 5 rotations
Okay.
every second.
Okay.
So if we cancel out our seconds, then this is saying that, so the physical significance of those units is it's saying that you have to constantly apply that much, whatever it was, 0.942 Newton meters. You have to constantly apply that much in order to rotate that system.
Every extra amount of rotations, or is it just for every rotation itself?
Continuously.
Okay.
Continuously,
Okay.
yeah. Yeah, so this is not based on time anymore at all.
Yeah.
So as far as the rotation question goes, yeah, I guess.
It's more clear now. It's just
Okay.
like radians, like, I don't know, it just didn't make sense to me at first, like the way, like, I'm used to units like canceling out clearly, so like, when I saw that, my brain was just like,
Right. Maybe a good way to think about it would be if we had like 30 1/seconds, like hertz,
yeah,
that would mean 30 rotations
yeah,
in 1 second, right? So 30 radians per second is saying that you really have like those 5.5 turns
yeah,
every second,
yeah.
but you're expressing it in a different, instead of full turns, you're expressing it in those radian increments.
Okay.
Yeah, so it's kind of like a placeholder unit
Gotcha.
that just disappears as
Okay.
you work the problem.
So in the end, it doesn't, it's literally just Newton meters.
Yeah, in the end, yeah, there's no, you just want Newton meters in the end. Yeah. All right. So part B to this problem is one that I never really got to work fully before I got here because I wanted to work the other ones. Anyways, yeah, I ran out of time to work part B fully, but I will show you what I did do. I just might have to go check it with Dr. Vassal and make sure I'm explaining this well. Oh no. So, okay, so we have a pipe, right? No, we don't. No, we do not.
Sure.
Trick question, yeah.
See if you're a fan.
Okay, so
I would-
that was a test.
Yeah.
Y'all passed.
And with the classic professor response.
Yeah.
I made that mistake intentionally to see if you guys were paying attention.
That's right.
Yeah, literally.
Okay, so we have these two discs, and we have this fluid, right? That's between them, and so if we're looking at, this guy's rotating at, actually this one's stationary, so this one is omega equals 0, and this one was omega equals 20. Okay, so what you're going to end up, oh, you know what? I'm thinking of a totally different problem. Yeah. Yeah, I had a whole different problem in mind. That's why I got confused with the pipe thing. But so if you were looking at this and you had your equation, where'd it go? Yeah, this guy, this M equation, then we know that the force or your torque M is related to that thickness T. And so you could use something like MATLAB or Excel. And you could generate a table of values, you know, and then you could plot a bunch of points. It wouldn't look like that, you know. It might, just as an example, I'm not saying it looks like this, but you know, you might get something like, you know, you might get a force profile, maybe like that or something. So anyways, not saying it looks like that. Yeah, not accurate. But you could plot your points and see what those torques are.
I'm guessing that's not a test type question.
I wouldn't think so. Yeah, I don't think he's. Yeah, I don't think he's gonna. Yeah. He might have you like draw a profile, like a rough profile.
Yeah.
But in this case, he said plot. So what came to mind for me is that you get MATLAB or Excel. You know have your equation, plug in your T's, and then figure out what your M's are and where they're at and stuff. So. All right, problem 3. So now this is where the homework starts.
Okay.
Yeah, so this is your homework assignment 1, number 1. And what time do we have?
You got about 7 minutes.
7 minutes. Cool. Time flies. Okay, so I'll let y'all give me input. Do you want to do a certain problem from that homework?
What I was confused on was part B on this.
Part B on this.
Because I was like confused as we were getting closer to like, because the answer was the shear stress was greatest at the inner walls, right?
Yes.
So I was just confused on how, like, I understood it conceptually with how like shear stress works in the boundary. Like obviously as you get closer, you're gonna enter the boundary layer, and that's where shear stress is gonna be maximum, right?
Mm-hmm.
But I didn't understand it mathematically in terms of like how the derivative, the d dy changes as you get there.
I got you. Yeah. So I'll skip to part B for this one. And I'll talk to Dr. Vassal, but maybe coming back to these if anyone wants me to next week. So yeah. So part B, okay. So we want to know, where does the maximum shear stress occur? At the pipe's inner walls or the center of the pipe, and why? Okay, so let me draw a little picture here. Okay, so we have this pipe. Why do you not work for me? There it goes. Okay. So if we have a velocity profile, let's say our flow is coming in this way, right? And so we have some sort of velocity profile in this pipe. Then, okay, so you want to know where your maximum shear stress is.
And the origin was at the center of this problem, I'm pretty sure.
No, there was no specified.
Or was it for the second one? Because that's another thing that was confusing me is like, wouldn't this be based on where the origin too is?
That's what we thought when we initially did the problem. Because like, we were thinking if your origin's at the bottom, your max shear stress would be in the middle because it's your greatest change between velocity and height. And then if you were like right at the wall, it'd be 0 because your height is 0. And then if you went all the way to the top, your velocity change would be 0.
Mm-hmm.
But
Well, no, I see what you're saying. I do see what you're saying. I think the way to think about that is depending on where your coordinate system is located, that's going to change how you derive your equations. Right. So that's one of the fundamental assumptions when you derive something is where is your coordinate system so that when you're taking all these different distances and lengths, then you know what I mean?
You know what, if your rate of change is positive or negative pretty much.
Yeah, you know where your rate of change is positive or negative. You know, like for example, if we were in the middle, like let's say we put our coordinate system down here or something, then that distance is going to be different than if we locate it here.
Yeah.
You know, so it's going to change the characteristics of the problem and how you derive it.
And that's kind of what we're curious on is like, if it's at the bottom, right, then the maximum shear stress would be in the middle, correct? Or would it still be at the inner wall just on the top?
It would still be at both inner walls.
Really?
Mm-hmm.
Even though they're fixed?
Yeah, so
that's what I didn't understand, at least. I can't speak for him, but like my interpretation was tau is dependent on viscosity and du dy. So I was
Mhm.
confused if, because of the no slip condition, the velocity is 0 at the walls, how it would be, like tau would even exist there. You know,
oh, I see what you're saying.
it's
Yeah.
like if the velocity is 0, then wouldn't tau also be 0 at the walls? Because they're fixed and the no slip condition says that the
Right.
velocity is 0 there.
Yeah. So yes, I think you're onto something there. Yeah. So if we zoomed in right here, so I guess a good thing to keep in mind is that if you change your coordinate system, which changes how you derive the equations, that doesn't change the physics underlying what's happening.
Mhm.
So your max shear will still be at those points.
Yeah.
But to your point, if we were to zoom in on this section right here, this pen is struggling. I put batteries in it like 2 days ago. Okay, here we go. I need a new pen for some reason. This one's not doing it. Anyway, so if we really zoomed in and we like had our velocity profile, you know, like this. So you're right. If you looked directly here, your V is equal to 0 because no slip. But right here, right here, V does not equal 0. And the thing oh no, you're good. I was going to say the thing to note is that in this shear equation, you're not looking for velocity. You're looking for the rate of change of velocity.
So
Yeah.
it would be better to think about it more in terms of like the boundary layer where it's going to be big rate of change until it kind of like levels off and it has like a constant velocity.
Right.
Okay.
Yeah. So if we were looking at this and this is our boundary layer, let's say, or something, the boundary layer is where you have the most drastic shear effects. So if you're thinking about just physically that if the boundary layer is where you have the most of these shearing effects, then that's where your maximum rate of change of velocity is in that area where there's a lot of dynamics going on.
Sorry, another question, but
Yeah.
so before earlier, right, you said shear, it occurs between a solid and a liquid, right? In the case of fluid systems.
Mhm.
So is there any case where it would occur at the center of the pipe? Because like center of the pipe is just liquid on liquid, right? So like
Yeah.
how does shear work at the center of the pipe? Like how does the profile, like does shear exist outside the boundary layer?
Yeah. So yeah, shear can exist between liquid and liquid interfaces too. Yeah.
Okay.
Yeah.
Because that's also part of what was confusing me is like looking from that, right? The vectors are obviously the largest at the middle. So if your coordinate system was from the bottom, I would feel like the velocity versus the rate of change at the middle would be, or the change in y at the middle would be like greater than the velocity rate outside that boundary layer, because the velocity is going to be like a very, very small number, right? Like right outside of that boundary layer inside of it.
So
Yeah,
it's
you mean like right here?
Yeah, like basically like
Right.
right before you hit that no slip condition, it's gonna be a very, very small, velocity, and then it would be a very, very large Y. So that's why I was kind of confused on like why it wouldn't be in the middle, because in the middle you have a smaller Y and a larger velocity.
But it's, so it's the derivative, right? Because it's
Yeah.
the tangent line, and as it gets closer to the wall, it's getting more extreme.
Yeah, that is what got me about this problem as well when I was first looking at it, is that because I thought the same thing when I was just first thinking through it, like, wouldn't that zero velocity make a difference, kind of thing? And I know you're talking about coordinates too,
Yeah.
but yeah, I think, instead of thinking about it in terms of velocity, what we're looking at is, do this. What we're looking at is these tangential lines, these rates of change. And so your shear is being determined by how drastically is your velocity changing in that region. And so when you have that no slip condition that's actually stopping the fluid particles in contact with it, then you're having some pretty major changes in the velocity profile in that region.
I have so many questions.
Okay, yeah.
I get that.
Yeah.
But then like now if we're going based off the tangent line, because that makes sense, right? It's the derivative, what's the derivative is the tangent line. So like that all makes sense. But like then when you reach the peak of the parabola, does that mean that there's no shear stress in the middle or minimal shear stress in the middle? Because your tangent line is pretty much vertical.
Mhm.
So would that mean that there's almost no shear stress in the middle of this pipe in this case?
Right, very little.
Okay.
Yeah,
Okay,
very
so
little. Yeah,
basically be
yeah.
like tiny bit of shear stress in the middle, and then it just increases exponentially to get it outside.
Yeah. So, right, when you have flow, like if you think of these as fluid as a bunch of layers of liquid, then as it's flowing, the fluid is flowing and kind of interacting with the other layers. So there's still shearing happening as these fluids are, unless they're traveling at the exact same, rate.
Yeah. Which is pretty much impossible, because that's what laminar flow is, right? Is when they're traveling at the exact same rate, and that pretty much never exists.
Yeah, it's very rare. Right, very rare. Yeah. So, and viscosity is playing into it with the shear, which this is all one fluid, so your viscosity is constant. But I guess right here, technically, there is an instantaneous point of no shear.
Okay, that makes
but
sense. The tangential line makes a lot more sense now, like thinking about it in that terms of the derivative. Just the du dy, like I could not see it like conceptually.
Yeah, and I guess it helps me too, because I'm so used to seeing things in terms of like X and Y.
Yeah.
So Y here is like an X, right? So if you had like plotted this, what we're looking at is something like this. If you flipped it in terms of what we're usually looking at.
Yeah.
And so it might be easier to see how that slope there. Oh no. Yeah, yeah. So like this, the slope here is like super steep.
Yeah.
Here it's 0.
Yeah.
Super steep.
Yep. And then once you get to the endpoints, it's the same exact thing. It's going to be 0 also because of no slip.
Right.
Okay. That makes sense.
Yeah.
That
helps me to think about it that way.
That was an A1 drawing right
there. Thanks.
When we did the problem first, we were just thinking it was like.
We like got it right away. We were like, all right, no slip. Next question. That was the easiest shit of our lives. And then we saw the answer, and we were both like, just mouths open, wondering what we did wrong.
What do you mean? Yeah. So, that's what helped me was thinking about in terms of rate of change instead of the value.
That's probably definitely helped a lot. And the tangential lines.
Cool.
It's almost like you're just your job or something. You're really good at it.
Yeah. Thank you. Thank you. Well, do you have any other quick? I guess we're out of time, but do you have any other questions?
Okay. Another day to get to or something.
I think today is chest day again.
Another chest.
Another chest day.
Oh, look at him. He's responsible.
Yeah.
We're not taking whiskey Tuesday.
Whiskey. Yeah, but you have to do it Whiskey Monday. We can't break the streak.
We only don't drink on that. I hate Jacob for understanding that right away. Like he sat there and he's like, "What do you mean you don't get it?" And I literally looked at him and I was like, I'm gonna shave your mustache off while you're looking. What?
Who?
Jacob, the genius. The one that's always wearing a bandana, like.
No, no, yeah, I know. I didn't hear you the first time
No.
at all.